Okay, guys, so we're going to move into dynamics of circular motion. So we're looking at dynamics now of circular. So dynamics deals with forces and such, so I'm just going to talk a little bit about it, and then you can read about it in more detail. But the idea is, last time we learned that if you have, let me undo that. If you have an object moving in a circle, so at constant speed, then you have centripetal acceleration towards the center. And if we have centripetal acceleration, that means that we have a net force. So we're going to have a net force as well in this direction towards the center. So we're going to have some net force, and we'll call that a centripetal force. Because it's always towards the center as we go around. So using Newton's second law, we're going to have this net centripetal force divided by the mass, and that would be my acceleration. So that's it. We're just applying dynamics, which is Newton's second law. Let's rearrange this though. So if I move the m over, I get that centripetal force. The net centripetal force, whatever they are, is going to be the mass times the centripetal acceleration. And then we learned last time that the centripetal acceleration is v squared over r. So we can change that. And now we have a new equation. So we have the centripetal force on a body moving in circular constant or uniform circular motion. It's going to be the mass times the velocity squared over the radius. And looking at this, then we can think about, the relationships between them. So if we do force over velocity, since the force, and this is velocity squared, so that becomes a quadratic. So we get a quadratic relationship like this. So the greater the velocity, the greater the force, and that makes sense. So just imagine swinging, you're standing there swinging a string, and you have like a rock on the end. The faster you go, the more tension in the string, the more centripetal force acting towards the center. The slower you go, the less tension. And then the radius, if we look at the radius, since radius is down below, that's 1 over r. So as the radius increases, we get a inverse relationship. That's a bad graph, but it basically comes like this. So as the radius increases, the tension is going to become less and less and less. And we'll do this in class. We'll swing some things around, and you can let it slowly. If you keep the same speed but let the radius start increasing, you'll feel less tension in your hand. That's basically it. So it's knowing this relationship right here. This is critical, and we're going to apply it to all sorts of things. So swinging things around in a circle. The other one that comes up a lot is going to be a car going around a bank. So if we have this circular turn, we have a car here, and the car is going to go around the turn. Then we know that there's a force pushing it inward. That's my centripetal force. That gives it its acceleration to curve it. So what we'll learn later is that force that's acting towards it is going to be the static frictional force. So the force of static friction. I should have done a little f. The force of static friction pushes it inward. And so what we can do is, instead of doing flat ones, we bank it. So we actually bank the curve. So you can imagine the curve is kind of going around like this. And so what we do is we bank it, and we'll see how that affects it. But that's a basic rundown of what you're going to learn in this section.